Hi, I'm Jason Lee from CMU, and this talk will be on deterministic mincut in almost linear time. This work was done while I was an intern at Microsoft Research, and I would like to thank my algorithms group for making this research possible. An alternative title for this talk is A Structural Representation of Cuts of a Graph. Later on, we'll see this connection more deeply, why the deterministic mincut problem requires understanding the structure of cuts of a graph. Let's begin with the preliminaries. In this talk, all graphs are unweighted and undirected, and we'll be considering the global mincut problem, which is given a graph, find the minimum number of edges to delete to disconnect the graph. One of the most well-known algorithms for this problem is the randomized contraction algorithm of Karger, which can be implemented in n-squared time by a result of Karger and Stein. A less well-known algorithm of Karger actually improves upon this all the way to near linear time. This is based on the two techniques of sparsification and tree packing. And in that same paper, Karger famously asked whether a deterministic near linear time algorithm exists. This problem seemed to resist all attempts for almost 20 years until a breakthrough result of Karabashi and Thorup, who showed a near linear time algorithm for simple graphs, which are unweighted graphs with no parallel edges. Then last year, the first progress towards general graphs was made by myself and Demalia Panigrahi. We showed that this problem reduces to polylog many exact ST-max-flow calls. And while we believe that ST-max-flow can be done in linear time, no such algorithm is known so far. So currently, this algorithm doesn't quite achieve near linear time. And finally, in this talk, we bypass max-flow algorithms altogether and solve the deterministic mincut algorithm in almost linear time. And this answers Karger's open questions from the 1990s. We do this by essentially de-randomizing the single randomized step in Karger's algorithm. And along the way, we'll see an important connection between de-randomization and establishing a structural representation of cuts of a graph. And by the way, most of the algorithms listed so far also generalize to weighted graphs, including our new result. But for simplicity, we'll stick with unweighted graphs in this talk. Before we present the algorithm, let's first briefly overview Karger's randomized near linear time algorithm, which has two main components, sparsification and tree packing. The first step is to compute a skeleton graph such that H is at most the size of G. The mincut in H is small. And if you think of the mincut in G as a vertex partition, then that same vertex partition H induces like a 1.1 approximate mincut in H. Then, given this skeleton graph, Karger shows that you can recover the mincut in G in near linear additional time. This algorithm works as follows. Compute a tree packing of a small number of trees into H. This is a packing of spanning trees such that no edge in H is congested too many times. And given this tree packing, we can show that one of the trees respects the mincut back in G. So recall it's a tree packing in H, but one of the trees in the tree packing in H also respects the mincut back in G. And by respect, we mean that the tree crosses at most two edges of the mincut. Finally, to recover that mincut, Karger designs an algorithm that computes for each given tree the minimum cut that respects that tree. And the nice thing about this part of the algorithm is it's entirely deterministic. So it remains to compute a deterministic construction of a skeleton graph. Karger's construction is by graph sparsification by random sampling, and he essentially computes a 1 + 1000 approximate cut sparsifier of the graph, which suffices as a skeleton graph. This cut sparsifier guarantee is only stronger. Let's now briefly overview the graph sparsification routine that Karger uses, which is by random sampling. Suppose we sample in each edge in G with probability roughly log n over epsilon squared lambda, where lambda is the min cut of the graph. Then Carter shows that with high probability, each cut is preserved in H within 1 plus epsilon of its expectation, which is here P times the cut in G. For the proof, he uses what I like to call a smart union-bound over all cuts, which means if we consider all cuts of size roughly n to the, let's say, n to the alpha, of cuts of size roughly alpha times lambda, then there are most n to the 2 alpha many of these, and each one fails with probably, say, 1 over n to the 3 alpha by a standard Chernoff bound. And finally, taking a union bound over all cuts of size roughly alpha times lambda, we get that the probability that any one of them fails is like n 1 over n to the alpha. And finally, we can union bound over all alpha to get a probability like 1 over n, which can then be boosted to any polynomial factor. And how we de-randomize such a result? Unfortunately, it turns out that even the verification problem is hard, since there are 2 to the n checks, 2 to the n cuts to check whether they are preserved approximately. In other words, the union bound of the proof is too inefficient, and if we can somehow union bound more efficiently, then at least for verification, there will be fewer constraints to check. So here our solution is to establish a structural representation of cuts, which will occupy the rest of the talk. And before we go on, I'd like to add that, in my opinion, this is one reason why we should care about de-randomization, and it's that it requires understanding the structure of target objects, in this case, the cuts of a graph. Before we discuss our structural representation, let's first go over previous approaches on the subject. The most well-known one is the spectral or linear algebraic approach, where we say that H is a spectral sparse variety of G if their Laplacians are spectrally similar. Here, spectral means that it's based on the eigenvalues of the matrices, this Laplacian to be specific. And historically, this approach had led to the first polynomial time deterministic sparsification algorithm due to Batsman, Spielman, Srivastava. And this has been shown to be able to sped up to near linear time by the work of Lee and Sun. And as it turns out, this is the only way of de-randomizing graph sparsification that we know of, namely understanding the structure of cuts in the spectral setting. And unfortunately, the best deterministic spectral approaches are still far from linear time. So in this work, we study an alternative approach, a combinatorial representation of cuts via this technique called expander decomposition. Now for the rest of the talk, here's a brief overview of what's to come. We'll first study the expander case, and here the main question to ask is what is a key property of expanders that makes them easy to solve? Next, we'll consider, after the expander case, we'll consider what I like to call expander of expander graphs, and these are the simplest generalization of expanders that still requires new techniques to solve. So this is the first step towards a full generalization. And finally, we handle the general case by a recursive expander decomposition, and we'll discuss additional challenges along the way. Let's first begin with the expander case, and we'll need a definition of conductance, which is this following expression. And the key property of expanders that we'll now exploit is the following simple statement due to correlation theorem. In an expander, any approximate min cut must be unbalanced, in the sense that the smaller side of the cut has at most alpha over phi vertices. So think of both alpha and phi as, let's say, polylog n. So the smaller side has the most polylog n vertices, which is relatively small. And given this simple claim, this immediately implies a very simple structural representation of near min cuts of a graph of an expander, and that's simply all the unbalanced cuts of this graph. This is a collection of cuts that covers all approximate min cuts. Now let's quickly prove this claim. assume without all generality that the volume of S is at most the volume of its complement. Then we can write the volume of S by definition as the sum of the degrees of the vertices in S. And now each vertex, we can consider the singleton min-cut around that vertex by just cutting off the edges around it. That is a cut of size degree of V, which must be at least the min-cut in G. So therefore this inequality holds. And finally, rearranging and using the definition of expanders and the fact that G is an expander, we get that the size of S is at most alpha or phi. And with this definition of unbalanced cuts, let's now try to build a sparsifier that only preserves the unbalanced cuts for now. And since the global min-cut is unbalanced, the global min-cut will be preserved. Our key lemma is that it suffices to ensure the following set of constraints. Here, the first constraint is that for each vertex in G, its degree is roughly preserved in H up to expectation plus or minus this small additive factor. Think of this as like small factor times lambda. And the second constraint is that for any two vertices U and V, the number of edges between them is roughly what we should expect, again, plus or minus this additive factor. Here we define the number sign as the number of parallel edges. And the nice thing to note is that here there's only n plus m constraints. Why is that? It's because the first one is clearly n constraints, and the second one is really only relevant for pairs UV that form an edge in the graph. That's because if U and V do not form an edge in the graph, then both of these quantities here will be 0, and therefore it's trivially satisfied. So in other words, we've compressed the union bound or the verification process to just these n plus m constraints. We've established a much more efficient verification process, which we later show how to de-randomize. Now let's quickly go through the proof of this claim. This claim requires the notion of a graph Laplacian, which is an algebraic representation of cuts. So here, for a given graph G, the Laplacian is a matrix whose rows and columns are indexed by the vertices, such that the diagonal entries are just the degrees of the vertices, and the off-diagonal entries are the negative of the number of parallel edges between two respective vertices. And the key property we'll be using in this talk is that graph Laplacians represent cuts well. For any set S, the cut induced by S is this simple expression here, where indicator of S is just a 0, 1 vector, where it's 1 if the vertex is in S and 0 otherwise. Now for the proof, let's consider an unbalanced cut S. Then we'll be writing the cut in H using this form here. Now let's imagine expanding the summations to get this. And by definition of a Laplacian, we get this. Now the key property is since S is unbalanced, this summation here only has alpha over phi squared terms. And now if we assume the constraints hold, then each of these is either p times the degree or p times essentially p times what we should expect plus or minus a small additive factor. And since there's only alpha or phi squared terms, the overall factor is at most epsilon times lambda additive. And finally, since the cut itself must be a size at least lambda, that's a multiplicative 1 plus S approximation. That concludes this proof, and then we'll see how we can get an algorithm out of this. So far we've reduced the verification step to just checking these n plus m constraints. To get an algorithm, we use the standard de-randomization method called pessimistic estimators. At a high level, the approach is to maintain probability upper bounds for each of these constraints based on Chernoff bounds, where we set P appropriately so that essentially the union bound over all the constraints is much less than 1. And now to construct a sparsifier, we loop over all edges E sequentially. And for each edge, we decide on the spot whether to add that edge to a sparsifier or skip that edge. And to decide which one we choose, we recompute the probability estimates conditional on whether we choose or skip E. And then we take the action depending on which conditional probability is smaller. So that essentially concludes the sparsification routine that only guarantees to preserve unbalanced cuts. So what about balanced cuts? Now, unfortunately, they can still be problematic for us. For example, imagine this graph here where G is a clique and H is this following sparsifier. It preserves all unbalanced cuts well, but for this balanced cut, it has only a single edge, whereas in G it has many, many more edges. Now recall our goal is to ensure that for the mincut in G, the corresponding partition in H induces a 1.1 approximate mincut. Now if the G is a clique, then the mincut is a singleton, but unfortunately here, the singleton is not a 1.1 approximate mincut in H because this balanced cut is so small in H. Here, our solution is to simply force all balanced cuts to have high weight. And we do this by essentially imagine overlaying an arbitrary expander onto the graph, lightly weighted, such that the min cut barely increases, but every balanced cut increases by much more. And that makes sense because the balanced cuts cut way more edges of any arbitrary expander than the unbalanced cuts. Now note that this doesn't give us a full 1 plus epsilon approximate cut sparsifier of the graph. In particular, the balanced cuts are not preserved up to 1 plus epsilon, but it still suffices for the skeleton graph construction for deterministic Mincut. Now, this is a brief recap of the expander case. And now let's move on to the expander of expanders case, where we define them as follows. We take our graph and we imagine having an expander decomposition of the graph, which is a partition of the graph into expanders. And we assume that if we contract each expander to a single vertex, then the resulting graph is also an expander. So this is what it means to be an expander of expanders. And once again, we want to study the structure of unbalanced cuts. But first, we need to redefine what it means to be unbalanced in this setting. And this becomes our definition. So consider an arbitrary cut S, and this time we first shift the cut to align with the expanders in the expanded composition. And let the set D be the difference of vertices once aligned. And now once we align the cut survives when we contract each expander, and we define the cut S to be unbalanced if first we shift a small number of vertices to align the expander, and then the corresponding cut after contracting expander, this cut S2, is unbalanced in expander sense. It is a small number of vertices on one side. That's our definition of unbalanced, and let's see why it implies a sparsifier for unbalanced cuts. So here, let's first define another definition. Let's first make another definition. For a contracted vertex in the expander, define V bar to be the pre-image of V, which is essentially the set of vertices that got contracted to that vertex, which is just the expander, the corresponding expander. Now we can define S, the set, original cut, to be the disjoint union of pre-images of the vertices in S2, set differenced with the set of vertices we shifted. And now we can apply again the Laplacian. We can apply the Laplacian property, and here the indicator of S translates to the sum of the indicators of V bars plus or minus for every vertex in the shift set indicator of U. And once again, there's a small number of terms of each in summation. And then we can do the expansion of over summations again and get that the final thing has like 2 alpha over phi squared terms of the following form, where each x and y is either a v bar or some u, either a v bar for some contracted vertex or some original vertex. And now we show that there are only O of n plus n many of these constraints that are non-trivial that we have to care about. And that's essentially because every edge E belongs to at most 4 of them, where for every edge, each endpoint is either the original vertex or the contracted vertex. There's 2 choices for each endpoint, and that's 4 overall. So once again, there's only O of n plus n constraints to check, and this implies fast verification and then also fast de-randomization. And finally, for the balance cuts, we essentially, instead of overlaying just an expander, we overlay an expander of expanders in the following sense. Finally, for general graphs, what we do is we compute a recursive expander decomposition of the graph, which is we compute an expander decomposition, contract each expander, and kind of repeat until the graph is like a single vertex. And now we require 2 properties of the expander decomposition. The first is that the number of intercluster edges is a small fraction of the number of total edges. Note that the intercluster edges are precisely the edges that survive after each contraction. So we want to show that they decrease by a large enough factor so that there is a small number of levels of recursion. The next property is more technical. It's called the boundary length property, introduced by recent work of Goranchi, Rake, Serenark, and Tan. I won't have time to go over this in this talk, but loosely is to upper bound the size of the cut as it evolves throughout the hierarchy. As we shift the cut and contract, we want to bound the size of this cut. So that essentially concludes my talk. We gave the first almost linear time algorithm for deterministic mincut. And one interesting question left open is whether a deterministic 1 plus less approximate cut sparsifier exists in almost linear time. And our approach doesn't quite get there, and the issue was the balance cut. So if we want to improve our approach, we have to look at how did the balance cuts work? How do we understand the structure of balance cuts? An alternative approach could be de-randomizing the existing fast sparsifier algorithms, for example, the one of Li and Sun. Another interesting direction to take is whether we can speed up this deterministic algorithm, mincut algorithm, to m times polylog n time, which would really match the best randomized algorithm time. And here, one major obstacle is we don't know any deterministic expander decomposition algorithms with polylog factors, in particular in m polylog n time. But even if such a result is assumed, that will still not give the full m polylog n time algorithm for deterministic mincut. And the additional obstacle has to do with this boundary linkedness property, which again, I don't have time to go over. And that's it for my talk, and thanks for listening.